Hi, I'm Marcelo Wanderley, a professor of music technology at McGill University, and I'm here to talk about the IDMIL Digital Audio Workbench, an interactive online application for teaching digital audio concepts. This is the work done in my lab, the IDMIL, with my colleagues Travis West, Josh Rohs, Eduardo Meneses, and Christian Frisson. At the bottom of the first slide here, you'll see the address where to get this application, where to try this application. So basically, this is about digital audio. Digital audio is everywhere these days, including mostly cell phones, and a lot of people listen to music through cell phones. So we have direct contact with digital audio. It's pervasive. So we need to teach as academics, but also we need to understand digital audio concepts. Problem with digital audio concepts, they might be more or less straightforward for certain parts, but they can become pretty complex because they involve audio, they involve mathematics, they involve signal processing, etc. So obviously there are several resources, mostly books, that go over this in several levels of details. But typically books are static, so they present parameters, you see the result, and that's it. You cannot really explore these parameters. To explore parameters, basically you go to laboratories. And so you set up equipment and you test what the effect of our manipulations are. Problem is, during a pandemic like the one we're living these days, access to laboratories is not easy. Furthermore, not everybody has access to laboratories at home, for instance, or to measurement equipment. So apart from the books, and here are some, and there's more on the paper, there's other examples of online tools actually to teach technical or scientific concepts, for instance, explorable explanations, but also interactive online simulations. Some of them are either even they do address digital audio, but from different perspectives. So the idea here on the digital audio workbench, basically, is to have this web application for experimentation of key concepts, mostly analog to digital, digital to analog conversion. So the idea is that you can experiment, change parameters, immediately see the effects, but also hear the effects. So it's free and it's usable anywhere as long as you have a web browser, Chrome or Firefox, typically compatible working recent versions. So design. It's again open, accessible. We show both time and frequency domain views of signals. So whatever you do in one domain, typically time domain, you see the effect in frequency domain. And we separate into three different views. So the first is sampling and aliasing. We focus on sampling. The second is quantization and jitter. So we focus on the effect of choosing a certain number of beats to quantize your analog amplitudes into digital values. And the third view actually shows all the panels and sliders. And this is more for a bit more advanced users who want to see everything at the same time. This is an example of the third view. And on the left side, you see the time domain panels. On the right side, you see mostly the frequency domain panels. So basically, they are one-to-one correspondence. What happens here in the time domain is what you see the effect on the frequency domain. And on the bottom, you have parameters you can manipulate, changing frequencies, changing sampling rates, etc. Also zooming, etc. We will see a demo of the second view, the quantization view, at the end of this talk. But again, the tool is freely available. Implementation details, there are several details on the paper itself, but the best is really to go to the source code, and then you can see exactly how this was done. It's basically, again, as a simulation, and there are some add-ons to typically what you could see in laboratory experiments or books. And for instance, this coloring of the spectra here, where samples from each multiple of the sampling frequency are colored in different ways, so that you can see which aliases are actually in the region of interest here between 0 and the Nyquist frequency, this gray region. Again, details on the paper and on the source code. We have used it in class last year during the pandemic, and at a digital audio course, entry level, so typically first year of music technology, undergraduate class, with students from more technical and less technical areas, from music, from engineering, etc. So it's a mix of different populations. And it was used in class and in assignments. And basically the feedback you got is that students really felt way more engaged with the topic by being able to try themselves manipulations of parameters and seeing the results. As obviously this is an ongoing work, there are several features we want to implement, and one, for instance, is being able to record the output of the sound, the simulation, so that we can then analyze further analysis. But there are several others, embedding, etc. So this is a very short introduction. There will be the demo now, and I'd like to thank you for your attention, and we're open to questions. This is the address where you can try the tool, and this is the source code. And thanks for funding from the NSERC, the Natural Sciences and Engineering Research Council of Canada, discovery grant I got a few years ago that actually partially funded this work. Thank you very much.